Hello, everyone. My name is Zhenghao Chen. I'm very excited to introduce my research topic, deep learning for visual data compression to you guys. I'm the PhD students under supervisions of Professor Dongxu and Wanli Ouyang in Electrical Engineering School. First, allow me to very quickly introduce myself about my education and working experience. I obtained my first class honors of information technology at computer science majors in the senior universities, and I was awarded Google Australian Prize for Excellency in Computer Science at the most outstanding honors in 2017. I was currently purchasing my Doctor of Philosophy degree at Senior University too, and my research is about end-to-end deep learning visual data compressions. And this research was funded by Australian government research training program, also known as RTP Fellowship. As an academic, I'm also very lucky to spend my time interning in different company organizations. My most recent internship is at SenseTime Group, which is the largest AI unicorn. And my research was facial attribute recognitions and produced one paper in ICME 2021 oral and one US patent. I'm also very lucky to interning in Chinese Academy of Science in China and CSIO in Australia, so in which I did a research about domain adaptation-based object detections and time series data visualizations. Now I will give more details about my research topics, which including one overview, motivations, and three selected papers, which I'm being most proud in the computer vision and compression fields. So I have a very broad research interest in computer visions and machine learnings. Particularly, I'm resolve the computer vision problem, particularly low-level problems using the deep learning techniques. So I'm mostly concentrating on developing the end-to-end optimized learning frameworks for video compressions. So now I want to give us a simple motivation why compression is very important. So in nowadays 5G areas, so we transmit and storage a lot of data in our clouds. And most of data is the visual data, such as images and videos. Assuming we have uncompressed images with 7,000 and 5 times 5,000 resolutions, and it typically costs up to 120 megabytes without any compressions, which means if we have uncompression standard videos with 60 FPS and 1 second with such frames, it will cost up to the 7.2 gigabytes. And this will cause a disasters for your servers. However, if we can introduce effective lossless compression techniques, it can compress this video to about 3 times smaller using the lossless compression techniques, while the 10 times smaller in the near lossless formats using effective lossy compression such as JPEG or JPEG 2000s. So it plays a very important role in the media streaming, online conference, and data storages. Now the next question is, why we need to introduce the learning-based compression rather than directly adopting the current existing coding standards? We have 2 motivations. First, using learning-based compression techniques allowed you to optimize your coding frameworks based on a large-scale data with more specific domains such as medical images, automotive stereo image domains, and which normally have much better compression performance than the existing standards. For example, in our latest publication, exploiting Intra-Slice redundancy for learning-based lossless volumetric image compressions, our learning-based method outperformed the traditional compression methods JP3D, which also known as JPEG 2000 Part 10, in 1 MRI domains. And our methods achieve much more better in the lossless compressions by optimizing based on the medical images. Second things, The learning-based compression techniques allowed you to transform or encoding your obtained raw data into better distributions for the various machine vision tasks, such as prediction and detection, as well as cost smaller storage. For example, once you query a raw data from surveillance, using the effective learning-based compression techniques, you can obtain much better distributions for different machine learning tasks without decoding these data, while have much more better reconstruction performance for human perceptions. Now, I will introduce 3 of my most proud papers in learning-based video compression formats. The first paper is called Improving Deep Video Compressions by Resolution Adaptive Flow Codings. So this paper has accepted by ECCV 2020 as oral presentations, and I will serve as the co-first authors. So this work proposed a resolution adaptive coding for better compressing the introduced motion patterns, which is mostly the optical flow. So in which we propose 2 schemes. The first, RFC front. In this scheme, we investigate the front level's resolution adaptive coding strategy, in which we select the optimal global motion patterns for motion compensation based on the RD criteria. Second, RFC block. We also investigate the block level resolution adaptive coding strategy, which is inspired from impact. So we select the optimal local motions in different region block. So our frameworks containing very basic modules such as motion estimation, motion codings, motion decodings, motion compensations, and residual codings. So this is nothing different from any video codec such as DVC. So first, in our RFC fronts, we use this scheme to design the most optimal global flow maps for each video front. For example, if the video front with a very comprehensive global motions, we would like to choose the optical flow maps with the higher resolutions, which contain more information. While for the video fronts with much more easier patterns for movements, we will select the motion with the lower resolutions, which will cost less bits. Second, we proposed RFC block, in which we divided the motion patterns in different local region of blocks and using the different levels of blocks for each local regions. This is the detail of RFC blocks. As you can see, we're using 2 levels. For level 1, we're using the larger scales of blocks which contain much more information for each movement patterns. While for the level 2, the block size is smaller, but it costs much less bits. So level 2 is obtained by just simply doing the average pooling from the level 1. Assisting by indicating map. For example, we know that for the left side, we will choose the level 1, which will containing more movement information. Hence, this left side is more comprehensive movement patterns. But in a contrast, for the level 2, we know that we would like to choose the blocks from level 2, which is smaller, but cost less bits. So combining these two, we can obtain the final reconstructed motion patterns. And using these overall schemes, we can intuitively obtaining the most optimal optical flow with the most optimal rate distortion value. So in the 2020 video compression benchmark, our method, which is denoted as this straight lines in the black, achieved the much more better compression performance than the other methods, such as H.264 and H.265, and other learning-based compression methods such as DVC, and one method proposed by Disney Research. So this is the very simple demonstration videos. So as you can see, our methods can use much less bit rate to compress the motion patterns than our baseline DVC. But however, our reconstruction qualities is basically the same in PSNR or even intuitively better. So this is the whole, so let's watch it again. Now I would like to introduce my second paper, exploiting intra-slide and inter-slide redundancy for learning-based lossless volumetric image compression. So this paper was accepted by Transactions of Image Processing 2022. And in this work, we propose a new intra-slide, inter-slide conditional entropy coding ICEC modules to model a long-term intra-slide, inter-slide dependency from the 3D volumetric images. And we also propose two new gating mechanisms, which are intragate and intergate, to more effectively exploiting the intra-slide, inter-slide redundancies. To the best of our knowledges, this paper is the first end-to-end optimized learning-based frameworks for lossless volumetric image compressions, which also achieved the state-of-the-art lossless compression performance on the MRI dataset and hyperspectral datasets. So in this work, we basically reformulate the lossless compression problems for the volumetric images. So given a volumetric image X with different digital slices X1, X2 to XT, so here this T denotes the length of the slice X. We aim to achieve the minimum cross entropy with real distribution QX, in which this X is just here, and estimate the distribution of estimate entropy model PX. So this is upon a very basic cross entropy coding theory. So however, directly estimate the distribution PX is way too comprehensive. So we further introduce the hierarchical latent feature ZTS on each scale index S for each slide XT. So now we reformulate the entire problem from achieving the cross entropy between the QX and PX to achieving the minimal cross entropy with real distribution QZ, in which this Z is the joint set of each individual hierarchical latent feature ZTS, and estimate entropy model, which is also distribution of PX, by using the following equations. So in here, we denote each slide XT as the highest scale feature ZT0, in which this 0 is the high scale index with the same resolutions of slide XT. So if we keep factorize this joint distribution PZ, we can essentially get a product of a series of individual conditional entropy P ZTS given a set of features ZNN, in which each auxiliary feature ZMM is the feature which are already being encoded before the feature ZTS. However, in this, even though we can conditioning on all ZNM, but it's gonna be a lot of redundancies. So in this work, we particularly consider two conditions. The first is inter-slide conditions, and second is intra-slide conditions. For inter-slide conditions, we want to summarize all ZMN from the previous slide, in which the slide index M is less than the current slide index T, and the lower or the same scale, in which the scale index N is greater and equals to the current scale index S, and less or equals to the total scale index capital S. It can represent by using list formulations. And for the intra-slide conditions, we want to summarize all features ZNN from current encoding slide with the lower scale ZNN, in which the slide index N is equivalent to the current slide index T, and the scale index N is greater than the current scale index S, and less or equals to the total scale index capital S. So eventually we will have the following joint distributions, and you can see here, so this conditional entropy is meet above two conditions. Now the problem is the following equation is still unresolvable, because you can see for each individual conditional entropy, the number of the input variables is still dynamic. So this is unresolvables by using a fixed network. So we're introducing a latent variable HTS to summarize all feature JTS, which is including this feature JTS and all encoded feature JNN before this JTS. So in fact, once each auxiliary feature JTS is encoded, we can produce a correlated latent feature JTS, which is summarize all features of this JTS and all feature before this JTS. So in this way, we can represent inter-slice conditional entropies by using one latent variables, HT-1s, and summarize the all intra-slice conditional entropies by using two variables, which is one latent variable, HTS+2, and one auxiliary features, JTS+1. So I skip the mass derivative, but if you have interest, you can refer to the original paper. So in this way, we can reformulate these equations by using these equations. And in these joint products, for every single individual conditional entropies, we only have three fixed numbers of inputs. So to this end, we can embed such conditional entropies into the recurrent frameworks. So as you can see, at each scale, we extracted the auxiliary features JTS by extracting from the current slide XT by using a set of blocks, which is nothing but just very standard convolution neural networks, and then do the quantizations. At each scale, we directly deploy our inter-slice conditional entropy coding modules, ICEC, with the three input variables we mentioned previously. And the detail for each inter-slice conditional entropy coding models is shown here. As you can see, we use a bunch of blocks to produce the estimate distribution, which is the conditional entropy PJTS, and produce the most recent latent features, HTS+1, by simply encoding the most recent auxiliary feature, HTS+1. So this is the overall schemes to apply the previous conditional entropy we introduced before. To better filter the intra-slice features, we propose the intragates. So in which the intragate will filter out the useless features from the lower scale latent features HT+2 to the higher scale JS+1 by using dot multiplications and the sigmoid activation forwards. So this is inspired by very popular long short-term memory mechanisms from the RNN. And we also propose the intergate to better align the cross-slide latent features from the last time step T-1 to the current index T. So this in here, we use the metric multiplications to produce the global similarities from these two features. And then we apply these features with the similarity. So this entire architecture is inspired from the very popular attention mechanisms. So as you can see, our method ICEC achieved the best results in one large-scale MRI dataset, MRNet, which is proposed from Stanford universities in three different of the views: Excel, Corner, and Sector. And our method performed all 2D slice coding method PNG, JPEG LS, JPEG 2000s, and the 3D based image coding method JPEG 2000 Part 2, JPEG 3Ds, and the video-based method, which is HEVC families and FFV1, as well as the most recent 2D learning-based methods L3C, which is proposed in CVPR 2019. We also examined our frameworks into a hyperspectral data set, ICVL and CAVE. And our methods again achieved the much better performance than all other comparable methods. To better indicate our performance, we also query the private standard MRI dataset provided by the author Tim Burens, who is the authors of the most famous coding 3D image coding standard JPEG 2000 Part 10, which is also known as JP3Ds. And as you can see, in all three MRI dataset, our method ICEC is much better than the traditional 3D image codec JP3Ds for lossless compressing these three MRI datasets. So as you can see the results right here. Now I will introduce our last paper, LSVC, a learning-based stereo video compression frameworks. So this paper was accepted by CVPR 2022 with 2 strong accept and 1 weak accept. So these frameworks reduce the both interview and interview redundancy by iterative performing the deep motion and disparity compensation in feature space for both left view and right view videos. So particularly, we propose 2 compression scheme, MRC and DRC, to compress the residual motion compressions and the residual disparity informations. To our best knowledge, so this is the first end-to-end optimized stereo video compression frameworks. So our frameworks iteratively compress the right view frame XR and left view frame XL using an iterative compression scheme from the time step t to t+1. So for to compress the current view of each videos, we conduct both motion and disparity compensations. So let's see in more detail. For example, in our LSVC left view compression modules, to compress the current frame XTL, we use the reconstructed frames at the left view X hat LT-1 as our within view reference to conduct the motion compensations with motion estimations, motion residual compression, which we'll introduce later, and motion compensations for the entire motion branch to reduce the temporal redundancies, as well as we were using the reconstructed left view frames at the same time step t, which is the X hat RT, as our cross view reference frame to conduct the disparity compensation branch, which including the disparity estimations, disparity residual compressions, which I will introduce later, and the disparity motion and disparity compensations to reduce the binocular redundancies. So we produce two features, the temporal features from the motion branch and the disparity features from disparity branch. And we're using a fusion networks to obtain our final predictive features here and to subtract with our original features extract from our current frames. So in this way, we only need to compress the residuals to reduce the both temporal and binocular redundancies. And we directly adopt the learning-based lossless entropy coding methods to calculate the bit rates from the bit strings of the motion disparities and the residual features. The right view compression modules is almost identical to the left view, except we using the reconstructed left view frame from last time step t-1, which is the X hat LT-1 as our cross view reference to conduct the motion compensation disparities, which include the disparity estimations, disparity residual compressions, and the disparity compressions. So these features will have the mismatch for both the time step t-1 to t and the view difference L to the left to the right. So in order to overcome these issues, we aligned it before we conduct the disparity branch, in which we simply use the deformable warping to warp the feature, the left view feature t-1 to ft to reduce the temporal mismatch. And the second difference is we did not use the motion residual compression when compress the motion patterns because the motion is not really in this stage. So we directly employ a very famous deformable warpings with the offset map and reference features to predict the light features. And we apply this scheme for both of our motion compensations and disparity compensations to produce the temporal predict feature here and disparity predictive feature here. And simply using a concatenation framework with a concatenation and a standard convolution and red block to produce a better, more accurate predict feature F bar T. So for more effectively compress the motion patterns and disparity patterns, MT and the DT, we propose the motion and disparity residual compressions, MRC and DRC. For example, in our MRC, for compress this current motion offset MT, we adopt the reference offset reconstructed from another view. For example, this MTR from the right view to predict the current motion offset from left view MTL, assisting by the disparity information. So in this way, we only need to compress the residual information between the predicted motion offset features from this MTR and the raw offset motion feature from this MTL. So these residuals cause much less bit rates than directly compress these raw motion informations. So similarly, in our disparity residual compression DRC, we're using the disparity offset from last time step T-1 to predict the current disparity offset DT, assisting by the motion informations. So in this way, again, we only need to compress the residual information between the predicted motion offsets and the raw motion offsets. So this residual disparity informations is much smaller than the raw disparity informations. So this is some demonstrations for our MRC and DRC. As you can see, our predicted motion informations is very close from our MRC modules is very close to our raw motion informations produced from our motion estimation modules. So the residual is much smaller than the raw information to be compressed and consequently save much less bits than just simply compress these raw informations. Similarly, in the disparity offsets, we see that the predicted disparity offset is very close to the raw disparity offset produced from the disparity modules. So their residuals is much smaller than this raw information for compressions. So instead, we compress this residual informations than this raw informations, which will save much bit and be more effective. And our result is also quite impressive. We include in the traditional single view codec H.265, which is HEVC, and its multi-view extension MVHEVC, and the most recent state of art codec FVC to compress it. So now let's have a look at our results. So our method actually achieved the pretty impressive benchmark results for the automative stereo video compressed benchmarks, in which we include the traditional single view video codecs using the H.265, which is also known as HEVC, and its multi-view video extension MVHEVC, denoted as a purple lines. We also included the most recent state-of-art learning-based video compression methods, FVC, published as CVPR 2021, denoted as the black lights. And finally, our methods, LSVC, denoted in the red lights. So as you can see, our methods achieve the better results than both learning-based video compression method FVCs and the multi-view video compression method MVHEVCs for both PSMR and MSIM in the Cityscape datasets. So I also like to mention that I only tune our models in the Cityscape dataset, but we not only achieve the best stereo video compression performance in the same domains, we also test it in the different domains, KT 2012 and KT 2015, using the model tuned based on the Cityscape data sets. So as you can see, our method also achieved the best stereo video compression results than all other three methods in these two cross-domain data sets with a very distinguished gaps for both PSNR and MSI measurements. So basically, our methods achieves very robust results for the automotive stereo video compression task by simply tune based on the single models. We also conduct some ablation studies. So in the first, we examine the effective of the left view compression modules and the right view compression modules. As you can see, so using only one compression modules can respectively improve performance from our baseline FVC did not using these black lights, and togetherly using the two modules together did not in this red lights can achieve the best results and are better than simply using one modules. Again, we conduct some ablation studies with our MRC modules and DRC modules. As you can see, simply using one modules, MRC or DRCs, can subsequently achieve the better results than our baseline LSVC without using neither of the modules. While combining these two modules, we can further obtain a better performance, which not is in this red light, comparing to only using one modules. We also test our codecs comparing to the other compression method, which are DVC, which is the first end-to-end video compression methods published in CVPR 2019, and the DSIC, which is published by ICCV 2019, and it is the stereo image compression using neural networks. So it's not surprised that our methods achieve the better results for both PSNR and MSI measurements for these two methods. Because first, DVC is no longer the best learning-based video compression methods. It's even perform worse than our baseline FVC. While this DSIM, it only consider the binocular redundancy between two stereo image pair, but it totally ignore the temporal redundancy between each adjacent frames in each videos. So therefore, it achieved not really good performance for both PSMR and SIN comparing to our method, which considering both temporal and binocular redundancies. So these are some reconstructed results. As you can see, our method LSVC achieved better reconstructed performance with this certain frame in the two cases, and achieve the less bit rates than the MVHEVC, FVC, and H265. So now let's have a look our demonstration videos. So as you can see, our method LSVC achieved the less bit rates than our baseline FVC, while we have a better reconstruction in terms of PSNR measurement metrics in basically every single frames. So let's look at it again. So as you can see, our methods can still outline the digital BICE 5398, while our baseline FBC is already get all blurs for the reconstructive frame decoded from the compression B strings. So similar case happens in the second example. As you can see, our LSVC can still outline the details of these textures of each bricks, while our baseline FVC has already got all blurs, and you can basically see nothing for the textures in the reconstructive frame. Thank you very much for watching this presentations. So if you have a more interesting about me, you are also welcome to browse my personal websites. And I have denoted everything I just speak in different sections. And I will be very excited to hear from you. And thank you again.